Yeah, our speaker tonight is Mark Darrach, who's a botanist. He's a geologist. He's a man about town. We're putting the meeting together. I said, "Oh, yeah, I'll give a talk," but I thought, well, it'd be nice to have a kind of a geology sort of talk, and that was going to be our plan when we were going to try to do the meeting last year. So I thought, Mark knows geology, and like any good field botanist, you have to be a geologist to really do plant work, or it certainly helps. I met Mark years ago. We both had a little bit darker hair then, and we share a love of dogs and being outside and rare plants and all that. So Mark's going to talk tonight about geology and how it's important for plant species, and led the field trip, or helped lead the trip today, the Blue Mountains. I haven't heard report yet how that went, but I assume it seems like everybody made it back, so didn't lose anybody. So anyway, let's give a big round of applause for Mark Darrach.
So click on. This is for the Zoom, right?
Right.
How does it work? There we go. Close enough? I'm properly Bluetoothed. Oh, goody. Okay. I'm going to adjust some things here. Yeah, we good? Everybody here okay? All right. So I'm both a geologist and a botanist. I fell in love with plants as a kid, particularly on the East Coast and the Pine Barrens of southern New Jersey. And that was going to be my path in life, I was pretty sure. But I ended up going to school at Oregon State as a botany major. And at that time, in the late 70s, it was a time when being a professional botanist and finding a job that was going to pay seemed a little bit sketchy. So I took a geology class, and I sat down next to a young lady who ended up becoming my wife. And she was a geology major, and I thought, I could be a geology major. I can do this. So I went into geology and kind of left botany on the side as kind of a hobby for the most part, but I still kept doing it. As years went by, I went through the academia route in geology, ended up getting into botany and geology as an intersection of the two sciences. And when I was working for a mining company in Montana back in 1989, and one thing led to another. Ultimately, I abandoned geology as a career and accepted botany as a career, and it was one of the best moves I've ever made. And the intersection between the two sciences is profound. It's absolutely profound. And so what I want to talk about for the most part is the interactions in the Blue Mountains of Oregon and Washington. So the whole Blue Mountain complex, essentially. I'm going to step out from the Blues a little bit and talk a little bit more about other places other than the Blues. But for the most part, that's going to be the scenario. Where is my... Oh, yeah, okay, thank you. There we go, okay. So the Blue Mountains, this is kind of a cartoon. It's the transparency on this is a little bit out of whack, but the Blue Mountains is usually considered to be about 6.25 million acres, mainly 3 national forests: the Malheur National Forest, the Umatilla National Forest, and the Wallowa-Whitman National Forest up here. Also a pretty good chunk of the Prineville district at Bureau of Land Management. Some people include the Ochocos over here, and I am including this piece of Idaho over here that's actually outside of the purple line, because geologically it's all part and parcel of the same story, and that's the Seven Devils Mountains. When people think of the Blue Mountains, they tend to think of the mountain ranges that punctuate the Blue Mountains. That'd be the Wallowas and the Strawberry Mountains and the Greenhorns and the Elkhorns. But really, the Blue Mountains, for the most part, are look more like this. And some of you saw this today from the top of Kamiak Butte, I'm sure, and when we were over in a near Anatone Butte and looked down into the Grand Ronde Range, you saw things that look very much like this. Lots and lots and lots of basalt, Columbia River basalt. And you can also see here that there's actually a little flat surface across some of these. It dips a little bit. This is the Blue Mountain uplift. There was a plateau here at one point. The Blue Mountains have uplifted, and that plateau has been eroded away and dissected by various drainages. This would be the North Fork of the John Day River down in here. But some of these places, like this little flatiron right here, still exist. And I'll return to that later on in the talk, but those turned out to be quite important in terms of the botany and the geology intersection in the Blues. So let me roll the film out a little bit and talk about the large scale of how the Blues came to be. The western margin of the continent used to sit right about here. And it was a complex margin. It was a passive margin. Everybody's probably heard of Pangaea, the continent that existed until about 250 million years ago and started to break up. Well, we've gone through the supercontinent cycle on this planet 4 times. Before the Pangaea supercontinent, we had the supercontinent of Rodinia. And Rodinia broke up and rifted apart. And when you rift the margin of a continent, it's not a straight line. It's not like you just straight piece and breaks apart. It breaks into all kinds of little bits and pieces and embayments and fragments and promontories. And as this broke apart, we ended up with a large ocean over here, the Farallon Plate, as it was called. And on the Farallon Plate, there were a number of island arcs that formed because of subduction that is occurring in oceanic crust going down under other oceanic crust, forming island arcs. Those island arcs were rafted along on the Farallon Plate. And there was a whole series of major terrains, Terranes, not AINS. This is geologic term for exotic pieces of crust that have been glommed on to continental margins. And we have the insular terrains, which are the outboard part of the story here, and the intermontane terrains. Many of these are actually now up in Alaska. If you looked at a geologic map of Alaska, it looks like a dog's breakfast. There's all kinds of stuff in there. There's all bits and pieces that have been slid up into and slammed into Alaska. But there's a promontory right here. And the Blue Mountains is actually this piece, this glommed onto and slammed into North America at about during the Cretaceous, roughly about 100 million years ago, thereabouts. And the Blue Mountains, I'm going to kind of zoom into a different scale here. And of those pieces of the Blue Mountains that came into and glommed onto the western margin of the North American plate, there was 4 major terrains: the Olds Ferry terrain, the IZ terrain, the Baker terrain, and the Wallowa terrain. And including the Wallowa terrain is part of the Seven Devils Mountains over in far western Idaho. Some of our oldest rocks in Oregon are down here in this area. They're Devonian in age, so we're pushing 400 million years old. Quite old rocks. And rather than these pieces being separate, they actually were all connected together by events that occurred outboard of the continent. So they came in basically as a whole chunk. It's not an IKEA situation where you have some assembly required. It's not. This was already essentially assembled when it glommed onto the western edge of the continent. Along the boundaries of these terrains are what we call suture zones. They're mechanical boundaries. They're essentially faulted boundaries. And in the boundary between the IZ terrain and the Baker terrain, we have some ultramafic rocks. And we've got some of those right here. And I'm going to back up one slide, because one of the things that is important here is that when terrains are rafted along on an oceanic crust piece and run into the continent, it's not a head-on collision. That's a rare situation. The only head-on collision plate tectonically that's occurring on the whole planet right now is where India is running into the Himalayas. And that's basically a head-on collision. But here we're having oblique collisions. Terrains are coming in. They're impacting the western margin of the continent, and they're getting translated to the north, but along major shear zones, major fault zones, kind of San Andreas style faults, really big ones. And we know this because we can actually look at the rocks in the Blue Mountains and all the rocks that are up in Alaska and so forth. And we can look at their paleomagnetic signatures. We can tell the inclination of the minerals, the magnetic minerals in the rocks. We can also tell what latitude they were at. So we know that the terrains in the Blue Mountains have actually formed all the way down here. They've been translated along these major faults all the way to the north, thousands of kilometers. And it's always been a bit of a mystery as to how this is going. And we're starting to get a pretty good picture now of how to piece this all together. But this movement of terrains to the north, many of which are all the way up in Alaska now, have been accommodated by these motions. But some of these motions are still ongoing. This is actually a geodetic map that actually is 24 years of satellite data, geodetic stations that are on the continent that are measuring through the satellite, are measuring how much displacement is actually occurring right now in real time. So these are all the relative velocity vectors, and you can see that there is a clockwise motion going on here. It's been going on for 100 million years. We've had clockwise rotation of a big chunk of the Pacific Northwest for 100 million years. And the places in the Blue Mountains over here, they've rotated 60 degrees clockwise during this time period. So we can roll that clock backwards, and we can undo that rotation and figure out the orientations of some of these structures actually used to be back a long time ago. But associated with this clockwise rotation, there's obviously got to be a place where that rotation isn't occurring. There's a boundary structure of some kind that's accommodating this, and it's up here in far northern Idaho and into western Montana. It's called the Lewis-Clark Shear Zone, and you see up here there really isn't any movement at all. And this is all moving. This stuff over here, this is associated with the subduction zone of the Juan de Fuca plate going underneath the North American plate right now. So you can ignore that. That's a different thing going on. The thing that's happening right here is this rotation that's happening. And another piece of the story that's really important here is the formation of the Yellowstone hotspot, which now sits right here and has migrated across. It actually, the hotspot itself doesn't move. This is a plume of magma and hot rock that forms down at the core mantle boundary, extremely deep in the planet. And it sits there stationary and essentially is like a little candle flame. And while the continent moves over top of it and burns a hole through it. So the Snake River Plain, which we are all somewhat familiar with, is this track of the Yellowstone hotspot. That hotspot first really broke through to the surface in a really big way about 17 million years ago. However, we have really good evidence that this hotspot actually existed back a lot longer than that. And there are bits and pieces where we see the hotspot was active, just kind of intermittently, not strongly active. And some of the, like if you've ever been to Smith Rocks around Terrebonne, Washington, there's rocks there. This is a caldera between 32 and 28 million years. There's the Tower Mountain caldera. These are all associated with this Yellowstone hotspot. But the real action starts at about 17 million years ago, when we ended up with a huge volume, just a ridiculous volume of magma that made it to the surface. Both rhyolitic, really violent magma, violent volcanic eruptions, and also a huge amount of basalt. And these are all of the various calderas that were formed across the Snake River Plain through time. And of course, we now have the Yellowstone caldera that's sitting right there that last erupted 600,000 years ago. So the Columbia River basalts is a huge part of the Blue Mountain story. I mean, this is just gigantic. Here is the actual full extent of the entire Columbia River basalts. It's about 150,000 cubic kilometers of erupted material, a lot of weight, a lot of volume. There are a number of other places on the planet that have this sort of thing going on, these flood basalt provinces. The Columbia River basalt province is actually one of the smaller ones. There are some like the Siberian one that's like somewhere in the neighborhood of 4 million cubic kilometers. which that particular event caused our Permian extinction. So what I'm going to do is kind of go through the different Columbia River basalt eruptive episodes as they are mapped on the ground. The first one breaks through to the surface here, and this is the Steens basalt 16.8 million years ago. And it's down here in Southeast Oregon. This is at the same time that there's the McDermott caldera has formed, which is silicic volcanism, rhyolitic magma, hugely violent. If you've ever floated the Owyhee River from Rome to Leslie Gulch, you will see the results of that large caldera. So the Steens basalt erupts first. That's the first thing out of the chute. The second thing out of the chute is the Imnaha basalt, which is a large part of Hell's Canyon. This is the basal bottom of the stratigraphy column of the Columbia River basalts for the most part. And that all flowed down the ancestral Columbia River drainage, at least partway. Then we ended up having the Picture Gorge basalts, which is actually a relatively small area, relatively speaking, down in the John Day area. And then the event really starts to get severe. We have the Grand Ronde basalts, which is what we're seeing, what we saw today in the Blue Mountains. Massive amounts of basalt erupting along northeast and north-south trending dikes, eruptive fissures that are very similar to what's going on in Iceland today, just as we're speaking right now. These flowed through the Columbia River drainage system all the way out to the coast. You've been out to places like Cannon Beach and places like that, those sea stacks out there. Those are Columbia River basalt that dive down into unconsolidated sediments that have been eroded out since, and that are basically the Columbia River basalts. And you'll notice that this particular eruptive event of the Grand Ronde basalts covered the whole Blue Mountain area, pretty much. However, things start to change when we get the Wanapum basalts, which are in the 15.3 million year old range. You can now see that the Blue Mountains, which sits right here, doesn't really have much of that basalt. The basalt laps up against the northern edge of the Blue Mountains, and that's because the Blue Mountain uplift had begun. We now have an elevated landscape, and it's above the eruptive events, and the basalt was not that deep. So this kind of gives us a time frame as when the Blue Mountains started to form. It really became truly Blue Mountains. Lastly, we got the Saddle Mountains, which have gone from 13 million to all the way to about 6 million years ago. It's not a very voluminous part. You can see 900, it's about 1,000 cubic miles, which doesn't, that's a lot. That's a lot for sure. But again, the Blue Mountains are already in existence here. There's some uplifts that have not been covered by these basalts. So when it comes to the Blue Mountains, we have a huge amount of volume here. And it's really affected what plants we have in the Blue Mountains. You think it's basalt, it's kind of boring. It's just lots of it. Not much in the way of variability, but that's not entirely true. Let's go back to the old rocks first. Here we have places down near the town of Granite, Oregon. This is the old rocks of, this is Permian seafloor chert, which is microcrystalline quartz, which settled out of solution in seawater, depths of maybe 3,000 meters. We're talking abyssal plain depths, extremely deep water. And this has been folded by tectonic forces, probably that occurred even before these terrains docked with the North American continent. These particular types of rocks, these cherts, the Elkhorn Ridge argillite is the name of this formation. And it's kind of a sterile formation. It doesn't have a whole lot of nutrients to give to plants. So there's not a whole lot that's going on in terms of supporting an interesting and diverse flora. However, the old rocks in general do have interesting chemical signatures that influence what rocks are, what plants are present. And you have a lot of calcic rocks that are fairly high in calcium. One of the groups of plants that really likes a calcic substrate are the grape ferns, the Botrychiums in the Ophioglossacea family. And that's where we find, on these old rocks, is where we find our most diverse suite of these plants. Botricium ascendens, Botricium pinnata. There's about 8 or 9 different species that are only down in that part of the Blue Mountains. We don't see them to the north because the basalt doesn't really support that sort of diversity in this group. The older rocks are also present at higher elevations, at alpine elevations in the Umatilla Mountains. And this is on a meta-volcanic substrate. If you've ever taken the tramway from Wallowa Lake State Park up to Mount Howard, you might have walked around up there on the trails. You probably would have seen this plant. This used to be a lomaceum. We now know from genetic work that I'm part of a team doing this work. It's actually a separate genus under itself. This is a monotypic genus. It's a single species, one genus, one species. I'll return to this plant later in the story. But this is a plant that's been sitting there stewing away. This is also an undisturbed area. It's never been glaciated. Through all the Pleistocene glaciations, it was never reset, essentially. So it's an area that's a very old surface. And those old surfaces turn out to be extremely important. But to go to a really lame map, this is the extent of, here's the Snake River over here. What do we have? Here's the town of John Day. All these little black areas are the ultramafic rocks, the serpentines and the periddotites that are mantle rocks that were part of what was glommed onto the North American continent back about 100 million years ago. This is the Strawberry Mountains here and the Aldrich Mountains a little bit further to the west. These ultramafic rocks worldwide are famous for having substrates that are really difficult for plants to colonize. They have high calcium, high magnesium, high iron, and they have a suite of other metals that are particularly toxic. Nickel in particular is a big one. Manganese is another. But they are really toxic to plants. So the plants that have actually learned how to live on this substrate, they're kind of stuck in almost an island biogeography situation where they're an island surrounded by things that are completely different. They're almost in a little ocean into themselves. So they evolved in place, and we do have some plants that are found only there. I also have some rocks here, and I'm going to pass them around. Some of them are a little on the heavy side. Oh, this is serpentine. This green, slimy looking rock. And this is periddotite, which is what turns into serpentine after it gets metamorphosed by seawater. And then I'll come to these three a little bit later on in the story. Just pass those around. These are when these rocks break down and form soils, these are the soils that support these unusual plants. This is a serpentine barrens in the Greenhorn Mountains, which is, oops, didn't want to do that. Greenhorn Mountains are right in here. That's that area. Oops. Wrong direction. What's going on here? There we go. No. Dude. Figure it out here. There we go. The serpentine barrens. These rocks, this is some of the green rocks right here. You can see there's not very much that grows on this. But there are some things that do grow on it. This particular dodecatheon used to be the genus. We have now moved that into the genus Primula in order to create a monophyletic taxonomic situation here. This plant is only 2 inches tall. There's no sense of scale in here, but those guys are that small. This has been called Dodecatheon watsonii. It would now be Primula watsonii. It has had a name in the past. It's a plant that probably should be looked into a little bit further, but it's, as you can see, it's a really attractive, just beautiful little plant, and it grows only on that serpentine there. This plant, Lomaceum tarantuloides, I specialize in the genus Lomaceum. I've described a number of species in the genus. This is found only on serpentine in the Greenhorn Mountains. It's a little narrow endemic that's found only there. This particular plant, you can't really see the lines on it, but the plant is over 90 years old. You can actually count these all die back to their root crown every year, and they leave a little annual ring behind. And you clean them up with a toothbrush and look under the microscope, you can actually count the rings on these things. I've seen some of these lomations that are 150 years old. But this one's only in the Blue Mountains, only in the Greenhorn Mountains, part of the Blues. And this is what the habitat looks like. There's other things growing in here as well, but not very much. You can see that rodents during the winter underneath the snowpack have been tunneling around, and this disturbance that they are creating is what keeps this plant alive. So when we lose our snowpack in a climate change scenario and that snowpack disappears, essentially, the pocket gophers that are doing this are going to go with it because they require that scenario during the winter. And that puts this plant in great harm's way. So this guy's probably going to go extinct in a climate change setting. This is a plant that needs to be listed under the Endangered Species Act. So those are the only two. Actually, no, that's not true. We got this one too. This is a member of the rose family, Potentilla versicolor, named after me by Barbara Erder, because I found it originally in 2002, along with a couple other of the folks that I worked with. It's found in the Greenhorn Mountains. It's also found in the Strawberry Mountains, it turns out. This is being genetically analyzed at the present time. It may be its own species. We don't know the answer to that yet, but it is a serpentine endemic. It's only on serpentine. Moving on to a different rock type that's present in the old rocks, looking at carbonates. This is actually a piece of carbonate from down in Nevada, so I'm cheating. I don't have any good pictures from the Blue Mountains. We don't have much carbonate, calcium carbonate limestone. We just don't have very much of it in the Blues at all. The only place that's really prominent is in the Wallowa Mountains and a little bit in Hell's Canyon. It's the Triassic age Martin Bridge limestone. And we do have a couple of plants that are big fans of a carbonate substrate. One of which is our only place in Oregon that you will find Pinus flexilis, limber pine. That's in the Wallowa Mountains at high elevation, and it's only on a carbonate substrate. It's only on the Martin Bridge limestone. Elsewhere in Western North America, this is a really common species at higher elevations, and it doesn't require limestone, but in Oregon, it requires limestone. Walt brought this plant up in discussion last night's talk. This is at Lime Hill, which is right at the intersection of where the Grand Ronde River dumps into the Snake. There's a chunk of limestone there. Again, we got the Martin Bridge limestone. This is a limestone obligate species. This is a Astragalus asotenensis, known only from Lime Hill and a population on the other side of Hell's Canyon that's also Martin Bridge limestone. But let's go back to the basalts again, because the basalts really control so much of what's going on botanically here in the Blues. And even though it seems like basalts are kind of boring, and most geologists say that basalts are kind of boring, and they are, I get it, but the plants don't necessarily think that way. So here's the whole enchilada of all the entire Columbia River basalt extent here in the Pacific Northwest. And this is pretty typical of what we saw today. Who was on the field trip with to the Blues today? We see cliff bands, slope formers, cliff band, slope former, cliff band, slope former. These cliff bands are columnar basalts. This is in Charlie Creek, which is pretty close to where we're going to be tomorrow for the field trip that we're going to be doing in the Blues again. We may actually get to see this view. It's pretty uniform looking stuff. However, there's more to the story. Here we have a typical lava flow. Not all lava flows do this, but most of them do. There's a thermal discontinuity in these large basalt flows as they cool down. And the bottom part, the massive column part, is called the colonnade. It's an architectural term. The upper part is called the entablature. And you can tell that this area here in this entablature, this is in the Columbia River Gorge, has a much higher fracture density, a lot more fractures involved. So this massive rock doesn't have much in the way of fractures. This has a lot of fractures. And this entablature right here is what controls a huge amount of the diversity in the Blue Mountains. Let me go back to this again. You can see that here's your columns. These are colonnades. These are entablatures, colonnade entablature, colonnade entablature. That is a really big part of the story in the blues. This is in Wheeler County, Wheeler Point, actually, in the far western edge of the Umatilla National Forest. And this is kind of you're looking at the boundary between columnar basalts. You're looking down on the columns here, essentially. But the rocks that are here on the surface, this is the boundary between the entablature and the colonnade of a major flow here. These are basalt scablands, as we call them. And when we were out today on the blues, we were actually walking on basalt entablatures for the most part today, with a lot of fracture density. Those are the places we saw some pretty unique plants. One of the ones that is restricted almost completely to these basalt entablatures is Phoenicallis curianthoides daguerreod, which we saw today out in the field. For a family, Brassicaceae, which doesn't have a lot of attractive plants, this one is super attractive. Really lovely plant. A perennial, don't know how long-lived it is, but it's a perennial item. Moving into the penstemon world, Penstemon gardneri, which we haven't seen yet on any of our adventures. This is another plant that is found almost exclusively on these basalt entablatures in basalt scablands. We also see Lewisia rediviva. In this setting, this is the primary place where you see, in the Blue Mountains, where you see bitterroot, Lewisia rediviva, and a very important plant for indigenous folks who dig the roots up and have it as part of their root feast every April. And it is almost completely restricted to these basalt flow entablatures. Lomatium caus, another plant that's found only in abundance anyway on these basalt flow entablatures. This has a little tuberous root, which is an important food for indigenous folks. So you can see that these entablatures are supporting a particular suite of plants that are important to indigenous people. We've got some cultural intersection here that's really quite important. This species is abundant in the Blue Mountains. We saw some of it today, but it wasn't in flower. Unfortunately, back in the early 1990s, these basalt entablature scablands, which often support this particular species of sagebrush, this is Artemisia rigida, rigid sage. Unfortunately, we ended up with an introduction of an annual grass. This is Ventinata dubia, North Africa grass, which is this kind of sickly yellow color here, yellowish green color. That has taken over almost all of the basalt scablands in the Blue Mountains, which is, yeah, probably talking 250,000 acres. Pretty big deal. And unfortunately, what this has done is created a flash fuel for fires where there was no continuity of fuels in the past. So this particular sagebrush species, this Artemisia rigida, is not a fire-adapted species. So when it burns, it dies and doesn't come back. It's over. And unfortunately, the Forest Service, in all their wisdom, or lack thereof, have done some controlled burns in places where they didn't bother to consult botanists at all, me and Joan, who I used to work with. And here's an example of them being proud of themselves for getting rid of fuels. And they've killed off, this is now barrens. There's nothing there at all, except for, you know, more of the Ventinata is still here. But this is what happens when this invasive grass has come to. We don't really know. We don't really know where it came from. We don't know how it started. There's not really good information on this. It's a really unusual, bizarre grass. It actually outcompetes cheatgrass. Yay, maybe not. But it does outcompete cheatgrass. One of the things that appears to be going on with this grass is it has an endobiont fungus that grows in the actual tissue of the grass, and it's a fusarium. And fusarium fungi are particularly notorious for being toxic. It apparently is an allelopathic grass, meaning that it kills off the things around it, including cheatgrass. Yes, it outcompetes everything. Ventinata dubia. Now we're going to move over to the shoulders of Hell's Canyon, also on a basalt entablature substrate. This is Lomatium filicynum, which I ran across on July 4th of 2010. when I was out there with my wife. We were camping with the dogs, and I was around botanizing as I tend to do, and I ran across this plant, and I realized this is new. What is this? Something completely different from that I'd ever seen before. Collected it, ended up getting it into a genetic database now that we've established for this large group of plants. It's actually a resurrected species. It was found by Marcus Jones in 1898, as I recall. Ended up in the Rancho Santa Ana Herbarium down in California, where it languished, although he did publish the name, it turns out, in a really obscure journal. We did not know that. We called it Lomatium basalticum when we published it. Jason Alexander at Jepson brought it to our attention that that plant had actually had a name in the past, so we had to rename it. But it's a rare plant. It's on both the Oregon and the Idaho side. It's probably a G2. It's not a common item at all. Another one that is tied strictly to these basalt entablature substrates with a little bit of soil on top here. This is Lomatium pastorale, and it is on the Walla Walla Ranger District of the Umatilla. It's found in about a 3 square mile area. It also requires rodents bioturbating the soil. So snowpack here, once it's gone in a climate change scenario, this species is going to disappear as well. And we've got very good evidence that's already going on here. Penstemon pinellianus, which we saw today, our lovely blue mountain penstemon. We saw quite a bit of it today. It's really pretty nice show of it. It's in perfect condition. This is also a species that's on basalt entablatures, almost completely. That I've never seen it on any substrate I would call anything other than a basalt entablature derived soil. Intersecting between the basalt entablatures of the blues and climate scenario. Here we have an intersection between climate and the basalt entablatures. This is a less windblown soil. It came off the ice sheet to the north, off the Okanagan lobe of the ice sheet, way to the north. Many of these areas got coated in a pretty good thick blanket of this fine silty soil, and supports grasses and so forth. It tends to be quite weedy these days, but because it was such a cold area during the Pleistocene, we had freeze and thaw cycles, freeze and thaw, freeze and thaw, freeze and thaw. We created patterned ground. We created basically polygons, frost polygons. And this is the boundary of one of these frost polygons. And this is part of an entablature of a lava flow as well. There are plants that grow strictly in these rock runnels, as we call them. In the Blue Mountains, we see Claytonia umbellata found only in that setting. That's a lovely plant. It's got a pretty wide distribution elsewhere, and it doesn't require this particular type of habitat elsewhere in its range. But in the Blue Mountains, that's the only place you find it. We also have a Lomatium species, Lomatium minus, which is found really only in that setting as well. Really attractive plant. Probably was used by indigenous folks. If you dig down through and move the rocks out of the way, you'll find a big old honking tuber down there. And early in the spring, when this is blooming, the peduncles of the inflorescence are delicious. They're really tasty. They're really, really good. I was introduced to this site on the Umatilla Indian Reservation by my Native American friend, Bobby Fossick, who's been doing a lot of distribution of seed to try and make sure that Lomatium Caus is available for the root crops, the root feast. And he was in this area on Esculpa Point and said, "Hey, I found a plant that I don't think I know what it is. Do you want to come check it out?" So I went to this spot, and this is, again, a real entablature sort of surface. And we found this. And this is a new Lomatium. We've got genetic evidence on it now. That's what, 6 inches, I think, thereabouts. So you can see this tuber is quite large. We don't have a name for this yet. I'm going to let Bobby name this, and we'll come up with some information as to how common it is. We think it's actually really rare. We only know it from the one spot. Another thing that the basalts do, which is something the botanists haven't recognized at all, which is really interesting, is down at the south end of the forest and also on the Prineville district of the BLM around the town of Mitchell and a little bit to the north of Mitchell, you'll see these large kind of rounded outcrops of basaltic looking rock. that are just different looking. And I didn't really understand what they were at first. It took me some time to realize that this particular suite of rocks has a different cooling history than any of the other basalts. And that cooling history has led to a completely different rock type. And here we have kind of gravelly sort of soil that is eroded away on top of this rock type. And these little white flowers right here are, well, actually on this particular rock type, you will see particular suites of plants that are found not only there, but mostly there. And this is one of them. This is Physaria occidentalis, which is actually pretty common, but it's almost always on that particular rock type. And you also see Astragalus diaphanous, variety diaphanous, and also variety diurnus, the rare variety. Also, just the minute you walk onto this rock type, boom, there they are almost every time. And you walk off that rock type, they're gone. So this little inch high or so, 2-inch high Cryptantha species is Cryptantha grandiflora. I didn't know what it was at first. I recognized there's something was different about it. I put it under the microscope, and I realized that even though it had been called Cryptantha intermedia in the past, it actually has a nutlet which is very smooth. Cryptantha intermedia has a tuberculate nutlet with real obvious bumps on it. So I knew I'd found something that that wasn't in Hitchcock and Conquest, wasn't in the Pacific flora of the Pacific Northwest. Got in touch with Ron Kelly at Eastern Oregon University, who's an expert in this group, went out in the field with him, and he looked at it and says, oh, you have found Cryptantha grandiflora. I've been looking for this plant for a quarter century. And it turns out to be quite common on this rock type. He just didn't know about it. It's well, the plants themselves are telling me what I'm on, but if I see an actual outcrop of it where it doesn't have a soil carapace on it, it's real obvious that it's something different. And so we have two different, we have basalt A and basalt B. And I'll pass around. This is your standard garden variety basalt with gas vesicles in it. This one is the other rock type, the one that has these unusual plants on it. And what's going on here is that these massive volumes of basalt are flowing across the landscape, and they're filling up drainages. And some of those drainages are pretty significant. And you'll get a pile of molten basalt that's 1,000 feet deep. Sorry, thank you. Yeah, you get a pile of basalt that's 1,000 feet deep doing in these places. And what happens is we get a process which is called fractional crystallization. It acts like its own little magma chamber. Rather than cooling really quickly like this basalt that's being passed around that has all the gas vesicles in it, doesn't have time to form minerals. It just turns into glass. Basically, most of what you're holding in your hands there is actually basaltic glass. It's like obsidian, which is a silicic glass, but basalt also forms a glass as well. And this particular rock that's going around is a gabbro. And it's got the same types of atoms in it. If I put a pile of atoms from that rock that's being passed around there, and this rock that's being passed around here, you'd have this roughly the same amounts of iron and magnesium and calcium and so forth. But because they're sequestered into different minerals, the rock weathers differently, the rock has a different chemical signature, and you get these different plants. This is a substrate that needs to be investigated more. There's undoubtedly some new species on this substrate that haven't been found yet. One of the plants that is found almost entirely on this substrate is this really beautiful mustard, Thelopodium mucosum. It's a G2. It's found in central Oregon in the Prineville BLM district. It's also in the Umatilla National Forest in a couple spots. And it's in moist spots. It likes wet spots, but it's wet spots that are on this particular substrate. Moving on to away from the lithologies, we have another way of looking at the landscape that's really important from a botanical standpoint, and that's looking at geomorphology, looking at the landforms. What are the landforms telling us? How do the landforms help control what plants are present on the landscape? This is on Rattlesnake Mountain, north of Tri-Cities in the bottom of the Columbia Basin. And you can clearly see that this aspect change right here from this lithosol habitat here to this more mesic habitat here has a completely different suite of plants, and it's all about aspect. That is not going to be the case in some places, but when you have aspect that's that pronounced, particularly in a pretty xeric sort of a dry setting, you're going to really notice that. I'm sure you guys have all seen that at some point, but you've got a completely different biodiversity signature here than you do here. This is another one that shows that aspect. In fact, tomorrow, hopefully we'll get to see a spot that's basically the scenario right here. This is on Bracken Ridge. I think this is the Lip Creek Road right down here, actually. And this is a north-facing aspect, and it's just this beautiful grassland of Idaho fescue. And this is where we find Silenes baldingii, the federally listed member of the Caryophyllaceae. The soils tend to be deeper here, they're richer. This is an area, this particular aspect is much more tolerant of weed infestations. It doesn't get hammered quite as bad. It does get hammered by the bovines, however. So this is a south-facing slope. You can see it's much more exposed. There's less soil development, and all these little patches, those are weedy patches that are basically completely reset and will probably never be native plants ever again. And that's all aspect landform based. Going back to this again, we see that the Blue Mountains uplift, and you can see these relatively flat surfaces actually dip a little bit. This is the Blue Mountains uplift. This is the area that's been uplifted. But these flat surfaces that remain from an old erosional surface that is millions of years old, those are places where you can hunt for relic flora, really old plants that have been around for a very, very long time. And tomorrow, if we get a chance to go out here, which I hope we do, you can see these flat tops. This is old Palouse Prairie that's uplifted in the Blue Mountains. And it's on these flat tops that we find things like Astragalus arthuri in abundance. We find the new phlox species. You find a bunch of things that you do not find on these slopes that have been eroded away. And that's where we found this. On June 29th of 2013, I was out with the Washington Rare Care Group, and we were looking for a new species of Pacra, that's Asteraceae, and that was our goal for the day. We found this instead. Walked into this population of this phlox, and I go, oh my goodness, this is either disjunct from God knows where, or it's a new species. Sent specimens off to Carolyn Ferguson at Kansas State University. She's the person who's been working in phlox for quite a long time. She wrote the Flora of North America treatment for the genus. And she got back in touch with me almost immediately and said, I've got one of these specimens in my collection. It was given to me by this guy named Stuart Marco 10 years ago. I didn't know what to do with it. I figured I'd never seen it before. And we found this population of it on Cape Horn Ridge. And one thing led to another, when we had ourselves a new phlox species. This is one of the first phlox that was new to science in this part of the world in 70 years. And it actually turns out to be not common, but what are we up to, Walt, now? Maybe a dozen populations? Another one that we actually went and visited on the same day that they came up to look at the phlox. We were going to go and try and see this today, but we just didn't have enough time to pull it off. This is over on the Idaho side. This is Phlox mollis. And that was also a species that had been kind of pushed off to the side taxonomically as maybe not a legitimate species. I think it had been considered to be just a hairy version of Phlox longifolia. But it's a very rare phlox, and it's just gorgeous. This would make a really nice horticultural plant. It's quite big. This is on Craig Mountain, and it's also, this is on that on one of these flat surfaces. It's on the Nez Perce Res. Some of these flat surfaces have wet areas as well, little basically snow melt, rainwater scenarios, because some of the rocks are fairly impervious. And this plant that's sticking up here is a Castanea paintbrush, which I had never seen before. And it's, I think, one of our most beautiful paintbrushes. It's actually genetically we have some issues with this, but it was called Castanea lutea. It was collected in the late 1890s by Amos Heller. And I realized, hey, this is something that is probably a new species. It wasn't. It was actually been recognized before. Since then, there's been some molecular work done on this this group of plants, and there are some questions as to what is what here, but I think it's absolutely a distinct item. It's as far as its signature out in the field, it's very different than Castanea cusickii, which has been what it's been equated with. Yeah, yep. That was actually one of the. Yep, yep. I have actually. I have been there. I have been there. Absolutely, and I'm hoping that if I can get to Cape Horn Ridge tomorrow, if that road's open out to there, everybody ought to be able to drive that. And we will actually see some of this. Is also on Park Ridge, which is on the other side of the creek. There's a couple spots in there. You've seen it a few times. Yeah, it's a gorgeous plant. Another thing that this is moving a little bit further afield, but it's talking about, I brought this up because this is a new genus. We just recognized new to science this year. I was down at Utah State University's Intermountain Herbarium in February, where I met Chris for the first time, wherever Chris is, there in the back. And going through their collection, annotating their specimens in the genus Lomatium, up comes this plant. And one of those sheets of three, there were actually 3 sheets from different places collected at different times by different botanists, one of which was Arthur Cronquist. And the age, the date on the specimen on the herbarium sheet said June something of 1934. And I thought, how old was Art Cronquist when he found this? He was 16 years old when he found this, but he just put the name Umbelliferae, which was the name for the family at the time, and called it good. It had been misidentified as Lomatium idahoense and Lomatium cusickii by the other 2 annotation labels on the other 2 sheets. But we took some material off of one of the sheets at the Utah State at the Intermountain Herbarium, ran it through the bioinformatics and sequenced it, and it came out to be a completely different genus, new to science genus, and its nearest relatives are that Geisleria greenmanii, which is up in the Wallowas, up in the high country of the Wallowas, and both of those plants' nearest relatives are on shale barrens in Pennsylvania and in Alabama, places like that. So you're talking thousands of kilometers away. That's telling you something about the biogeography of this particular area. If you look at Northern California and the Klamath country and Southwest Oregon, that's an area that's been ecologically stable for a very, very long time, many million years. It's developed a flora, a really rich flora unto itself. There was a plant that was discovered in 1990 by Glenn Clifton on the margins of Shasta Lake, and it was a shrub that he had never seen before. The sleuthing turned out to be in the genus Neviusia in the rose family. It's called Shasta snow wreath. And when that was found, they thought it was a monotypic genus. They thought it was the only one of the only species in the genus. But a little bit deeper digging, well done, Mark. They found that there was another Neviusia, and it's a Neviusia alabamensis, and it's in Alabama and in the Ozarks in Missouri, long ways away. There are also fossils in Neviusia from southern British Columbia from the early Eocene, so they're 40 plus million years old. So we've got a relic flora here that is still stewing away, that's left over from the Eocene. This is not a plant from the Eocene, obviously, but this plant has heritage that goes back that far. And this plant probably is the same story. So some of the Salmon River Mountains in central Idaho have relic flora that's many millions of years old. It goes back in heritage a long ways back in time for our eudicots. And this is that plant up close from being out in the field on the 6th of June, just earlier this month, with Don Mansfield and Jim Smith on Camas Creek, which flows into the Middle Fork of the Salmon. And we found two good sized populations of it. We now know of 5 populations of it. It's probably going to stay pretty rare, I suspect, but it appears to be completely confined to that drainage. So old surfaces mean plants that are pretty unique, and old areas that have been kind of undisturbed for many million years, same story. Plants that are related to things that are thousands of kilometers away. And I'll call it quits on that. Thanks. Happy to wave my arms and whatever questions may come up. Mm-hmm. Right, the entablature. Well, they don't break down to different chemicals. They break down into different fragment sizes because their fracture density is different. Chemically, they're the same. The boundary between the colonnade, the columns, and the entablature is a thermal boundary. That's the way the basalt flows cool. And that's how that happens. Yep. No. It is the texture of the soil, but it also is because if you got more surface area in those chunks, you're getting a weathering signature of those rocks that's a little bit different. So you may end up with some chemical difference associated with that too, because it's just weathering at kinetically, it's weathering at a faster rate. If you got a columnar basalt, that's not going to weather very quickly, and you're only going to end up with soil and the fractures and stuff between them. And there are some plants that live in that scenario. Lomatium laevigatum, this plant that I'll go way back in time here. That right there, that's in the Columbia Gorge. That plant, I'm going to point it out again. The reason that I have this photo is because growing out of this surface is a new Lomatium species, and it's growing into cracks. That's Lomatium saxarimus, which means rock fracture, and it grows in the fractures. It's been quite a long time since there's been a new plant species found in the Columbia River Gorge. This grows right next to Multnomah Falls Lodge. I mean, literally, it's just right there, which is kind of crazy. They don't eat it. It's a high silica grass, so it's not a plant that has much nutritive value, and the animals they don't touch it at all. They'll actually eat cheatgrass when it's greening up in the early part of the year. They don't touch it at all. Mm-hmm. Yeah, it's forming because the basalt is the basalt magma, the lava, the hot lava, 1,000+ degrees centigrade is pooling up on the landscape in depressions, like drainages and so forth. And when it does that, it's basically acting like its own little magma chamber. It's hot enough for long enough that the various atoms in that magma are able to assemble into the different minerals in that rock that you were holding there. When you've got a lava flow that is relatively thin across the surface, like this right here, it may not be particularly thick. It cools down fast enough that it doesn't give those atoms a time to align into in the minerals that you see in that rock we're passing around. And that, even though chemically they're essentially the same, the way they weather and the way the various ions are weathered out of those two different rocks is quite different. Yes. Yeah, ecclesia. It means church, for the Frank Church Wilderness. They are, well, and we found two of them right in that same creek. They were only 2 miles apart. And since then, we've gone back and looked at collections and seen what's been mislabeled, because we figured that Lomatium idahoense was the one that was probably misidentified as. It's been found in the lower Snake Salmon River drainage. And the other ones, I'm not remembering exactly where they are, because Don just really recently found them in the collections on the consortium website. But they're not terribly far apart from each other. They're not seriously disjunct. Oh, and the stuff that's in Pennsylvania and further away. Okay. Yeah, yeah, his question is he's not understanding the situation when you have Neviusia cliftonia and Neviusia alabamensis, and also Ecclesia graminea, and the plants that are very closely related to it over in Pennsylvania on shale barrens and so forth. What we're trying to say is that if you've got plants that are related to each other, that are that far apart, at some point there had to be an evolutionary scenario where there was actually a connection in the flora between them, and they're now separated by disturbances, ice sheets, whatever the case may be, over many millions of years that have separated those two pieces of the flora where they've stewed away separately but still exist. That, and then also finding that Neviusia was found in fossils that are 40 million years old, turned out to be, that's a timeline piece. It doesn't necessarily apply to the Ecclesia, but it may. It may. It's an old plant, and that part of the Salmon River Mountains hasn't really been disturbed. It's never been glaciated. It's not high enough in elevation to have ever been glaciated. Anybody else? Yeah. Ah, good question. Actually, we're talking apples and oranges, two different things. Yeah, her question. Oh, this is for Zima. I'm sorry, I apologize for that. She was asking if the Missoula, the Ice Age floods, have anything to do with the scablands scenario that I was talking about. They're two different things entirely. The scablands that we call scablands in the Blue Mountains and in the Ochocos and other places, as well as that, are just called scablands because they're really they're poor soils and so forth. So it's just a term that's used. Now, the channeled scablands that you see in Washington, that's all areas that were scoured clean by the Missoula floods. We call those channeled scablands, but they're essentially called scablands as well, even though the formation of them is a completely different scenario. Oh yeah, yeah, for sure. Yeah. The scablands on the Blue Mountains, these are all lava flows that were anywhere between 17 million years old and as young as about 15.3. But the channel scablands were anywhere between 15,000 and about 22,000 years old. Yeah. Yeah. Yeah, I think so. Yeah, the higher the fracture density, the more infiltration you can have of moisture, for sure. And of these big columns like this fracture density being low like that, you can channel water in those, and you end up with some seeps for sure in places like that. But the moisture distribution is definitely a bit different.